In this video, we will develop improper cubic point groups. Improper cubic point groups. So, this is part 11 of this series. In part 6, you have already developed proper cubic point groups. Proper cubic point groups means point groups with cubic symmetry, but without any improper operations, without any mirror or without any inversion center or without any 3 bar or 4 bar kind of operations. So, we found that there were two groups, that group 2 3, which was the tetrahedral group, which was group of proper rotations of a tetrahedron. So, that we developed, we will revisit them in this video, and 4 3 2, which was the group of proper rotation of a cube. So, both of these are considered as cubic point groups, but there are 5 cubic point groups and 3 of them have improper operations. So, those other 3 we will develop now. So, we will start developing them by starting with our proper group, which we have already met in, as I told you, we have already met in part 6. You can review that part, but here I am showing you the final result of that exercise, that the group 2 3 was the symmetry group of tetrahedron. Let me draw the tetrahedron again for you, and if you remember, it is nice to draw the tetrahedron with reference to a cube. So, we draw a cube and we properly choose 4 corners, 4 alternating corners of the cube to define our tetrahedron inside the cube. So, this is our tetrahedron inside the cube, and we saw that this had 4 3-fold axes and 3 2-fold axes. So, axes perpendicular to the edges of the tetrahedron or perpendicular to the faces of the reference cube were 2-fold axes, and axes passing through the vertex and the centroid of the opposite face, which happens to be the body diagonal of the reference cube. So, those axes were 3-fold, and these were the only symmetry operations. So, 4 3-fold axes and 3 2-fold axes. I have shown you only one each in this diagram, but in the stereogram we have all the 4 and 3-fold axes and all the 3 2-fold axes. We also took pains to develop the operations, and we saw that it was a group of order 12. So, there were 12 operations. So, 2-fold axes along the cube axes 1 0 0 0 1 0 and 0 0 1, they give you the 180 degree rotation called 2 1 0 0 and so on, and the 3-fold axes along the body diagonal give you the 3-fold rotations. Along each axis you have both 120 degree plus 120 degree rotation and minus 120 degree rotation, or you can call it 120 degree rotation and 240 degree rotation. So, there were 8 3-fold rotations like that, giving you a total of 12 operations in the group. Now, I want to just develop this group into 4 bar 3m. Now, I want to develop the 4 bar 3m group. So, I will develop it with respect to this figure. So, now if you look at the tetrahedron carefully, so we ignored, when developing the rotation group 2 3, we ignored any mirror planes or any roto-inversion axes which may be present in the tetrahedron. So, the first thing to note is that when you start looking for, or you start accepting that tetrahedron has improper operations as well, then what we had called a two-fold operation or a two-fold symmetry axis actually is a four-fold roto-inversion axis. Is a four-fold roto-inversion axis, because you can see that there are 2 points above, these 2 points which I am now circling, and 2 points below with respect to this axis. So, if I let us say, let me highlight, let me color this point as my starting point, and if I rotate by 90 degree, if it is twofold, I will rotate by 180 degree and I'll get there, and that is a point of tetrahedron. But if instead of rotating by 180 degree, if I rotate by 90 degree, I get there, and that is not a point of tetrahedron. But then if I invert it in the centroid of the tetrahedron, I will come to this point. So, which means this point, if this point was 1, this point can be mapped by a 4 bar plus or 4 bar minus, because I took a 90 degree rotation in the clockwise sense. So, this will become 4 bar minus along 0 0 1. So, you can see that the points are also related by the 4 bar axis, and 4 bar axis, as you know from your previous videos, has twofold as its subgroup. So, there is no problem, only thing is that whatever we considered as twofold are now becoming a 4 bar roto inversion axis. So, I will upgrade my stereogram by making these as 4 bar axis. The symbol for 4 bar has twofold included in it. You get 3 4 bar axis now. At the same time, if you look now, this plane of the cube, which I am now coloring red. Let me fill it with some highlight color to further emphasize it. Suppose you consider this diagonal plane. Now, tetrahedron has this mirror plane as well, because if you just see, if I label the points A and B, these are reflected, they are mirror images of each other in the mirror plane which I have identified. Similarly, if you label these points C and D, they are lying on the mirror plane itself. So, they exist where they are, but they also satisfy this mirror plane. So, this diagonal mirror plane, and the cube has 6 such diagonal mirror planes. In particular, this mirror plane, if I try to map in the stereogram, it will go exactly from in this direction, and there are 6 of them. So, I simply start adding them. My hand is not very steady, let me try to let it. These mirror planes are also passing through the threefold axis, as you can see, because they are going through the corners of the tetrahedron and corners of the tetrahedron, and they are also passing through the centroid of the opposite triangle. So, these mirror plane contain the threefold axis. So, that is why they are passing also through threefold axis. So, these are the 2 diagonal ones, the cube has 6 of them, accordingly the tetrahedron also has 6 of them, and I complete my stereogram by adding these 6 mirror planes. So, what I have developed now is the group 4 bar 3 M. This is called the TD group by Schoenflies 4 bar 3 M in the international notation. Now, if we want to do to complete the exercise of writing the operations of these group. For 2, 3 we had already written the operations in your previous video, and there were these 2 folds, 3 folds, which gave you 12 operations. Now, these 12 operations will double up to give you 24 operations when you are including these mirror symmetry and the 4 bar axes. So, let us just write them quickly. So, let me write the new operations in red. So, what we are getting now, you saw that we are getting 4 bar operations along the axes. So, you have 4 bar plus along 1 0 0 and 4 bar minus along 1 0 0. Similarly, about other 2 axes of the cube. So, 4 bar plus 0 1 0, 4 bar minus 0 1 0, 4 bar plus 0 0 1 and 4 bar minus 0 0 1. So, these 6 additional operations came because we identified that 2-fold of the rotation group is becoming 4 bar in the full group. And then we also saw that there are 6 mirrors. Each mirror gives you a reflection operation, which I denote by M, and since these are diagonal mirrors, their normals are of the type 1 1 0. So, I write M 1 1 0, M 1 bar 1 0, M 0 1 0, M sorry, let me fix this. M101, let me write M10 bar 1, M011 and M01 bar 1. So, 6 4 bar operations and 6 mirror operations gives you 12 additional operations, making you a group of order 24. So, that is the third cubic point group which we had. Let us now look at the full cubic point group. So, we discussed last time the rotation group of the cube, which was 4 3 2, and this is the stereogram of that. It has 4-fold axis, 3-fold axis and 2-fold axis. 4-fold axis along the parallel to the edges of the cube or perpendicular to the faces of the cube, as you wish. The 2-fold axes along the face diagonals and the 3-fold axes along the body diagonals, and we wrote the operations carefully and found that there are 24 such operations. Now, this was again done by ignoring the full symmetry of the cube, by ignoring the fact that cube has mirror planes or inversion center or roto inversion operations also, because we were interested in the proper group. So, this is actually the rotation group 4 3 2 is the subgroup of full cubic symmetry. Now, we are developing the full cubic symmetry group. So, we start with the cube. First thing which we ignored in the in our insistence that we will remain proper was, let us say, the inversion center. Cube had a nice inversion center sitting right in the center, because every corner of the cube can be inverted to an opposite corner. This symmetry was not there in tetrahedron. So, we did not consider, because tetrahedron is not a centrosymmetric solid, but cube is a centrosymmetric solid. So, it adds this center of inversion. And we also saw that any 3-fold axis with a center of inversion becomes a 3 bar axis. So, I am writing it roughly. as 3 plus 1 bar as 3 bar. So, all the threefold axes shown here become the 3 bar axis, and 3 bar axis are shown by a triangle with a hole. So, I am creating a little holes in all my triangles to make them now represent 3 bar. Then you also see that what we ignored in our discussion of proper groups was the mirror planes. Cube has nice mirror planes. So, for example, this plane you can see is a mirror plane of a cube. So, this is a horizontal mirror plane, and in the stereogram the horizontal plane is the primitive. So, I can color the primitive red to indicate that is a mirror plane now. But correspondingly you have two vertical mirrors also. So, if I add that on the stereogram, vertical planes in stereogram are the diameter of the primitive circle. I am adding two perpendicular diameter to represent these two mirrors. Also in this diagram is getting little messy now, but I think you can still follow. So, maybe let me change the color. Also you see that there are diagonal mirrors of this kind, and with respect to each face you will have two diagonal mirrors, and since there are three non-parallel faces of the cube, so you will have 6 such mirrors. So, let me draw these mirrors for you. So, these two diagonal mirrors which I have shown in the cube are these two diameters of the primitive. I am showing them in black, the same color, but now they are representing the mirrors. And there are 4 more. These are inclined diagonal mirror planes which go along these reference lines which I had already drawn. The reference lines which I used, now you know, the reference lines which I was using to draw my cubic stereograms were the actual mirror planes of the cube, but I didn't highlight them while discussing the proper group, because for proper group we don't consider these improper operations, but now these become the mirror planes. So, now my cubic point group is complete. This group is named M3 bar M in the international notation and OH in the Schoenflies notation. Now, this group also we started with 24 operations. We started with 24 operations in the 432, which was the proper subgroup of the cubic group, but this will now develop into 24 operations, 24 into 2, 48 operations of your full cubic group. So, let us do that. So, this becomes now M3 bar M. So, I will need to add operations, 24 more operations, which sounds a lot, but we can do it systematically by just noting what additional things we have added. And when we were adding additional things, we were not removing any symmetry which was there in the proper group itself. So, that is why I am keeping all the 24 proper operations as part of the group in the complete cubic symmetry also, but I will add now in red additional operations. So, let me add to this proper group, which was 432, another 24 operations which will make it improper or the complete cubic group. So, first thing to note was that we added a center of inversion. So, let me write that itself as one operation. So, center of operation 1 bar, but 1 bar converted 3 into 3 bar. So, along the 4 body diagonals, now I will have the 3 bar operations also. So, let me write them. 3 bar plus 111, 3 bar minus 111, and so on. So, we have 8 these 3 bar operations. Please also recall that we have added mirrors and we have added 9 mirrors, 3 mirrors in red and 6 mirrors in black in this stereogram. So, those 9 mirrors will give us 9 further operations. So, we will write them again, and mirrors are designated by their plane normals. Let me write the 3 axial mirrors first. So, M100, M010 and M001, and then 6 diagonal mirrors. So, M110 and so on. And when we have this 4-fold, this we had seen when we developed the 4 by M group, that now in the cube for each 4-fold. So, for example, the central 4-fold, which is the 001 here, the central 4-fold, there is a corresponding horizontal mirror, which is the equator. So, you have a sort of 4 by M subgroups in this cubic group. And when we wrote 4 by M, if you remember, 4 by M implies that there were operations of 4 bar plus type. So, noting this, we will have along the 3 axes, which are the 4 axes, also the 4 bar operations. So, we will now write 4 bar plus 100 and 4 bar minus 100 and so on. So, you can see in red we have now 24 operations. So, we have completed the group. We have so many operations and I have written so large you are not able to see the entire 48 operations in one go. Let me try to show, bring it. Yeah. So, these are the 48 operations of the cube. 24 proper operations shown in black and blue, which were also the operations of 432, and 24 improper operations which have been added now in red to complete the cubic group M 3 bar M. So, we have now developed 4 cubic point groups, 2 proper and 2 improper. A proper group of rotations of tetrahedron, proper group of rotations of cube, and complete group of tetrahedron and complete group of cube. But we are still missing one cubic group which need to be developed now. So, let us develop that group, the 5th cubic point group. This group is known as M3 bar. The Schoenflies notation, this is TH. And if we draw the stereogram of the symmetry of this group, let us do that. So, we draw the reference axis, it is a cubic group. So, we draw the primitive and our reference lines, which are the mirror lines. So, this group has 3 bar axes, and now you are quite familiar that where these 3 bar axes will be there, they will be along the 3-fold axes of the cube, that is along the body diagonal of the cube. and since these are 3 bar, I introduce little holes here to represent 3 bar. This also has mirrors, but this time this has only the axial mirrors of the cube, that is mirrors parallel to the faces of the cube. So, I have a horizontal mirror along the primitive and 2 vertical mirrors as diameters of the primitive. But now recall that whenever two perpendicular mirrors meet, the axis of intersection becomes a twofold rotation axis. So, here 2 vertical mirrors are intersecting, I get a twofold. Here a vertical mirror and a horizontal mirror is intersecting, I get another twofold, and a third twofold along the intersection of these 2 mirrors. So, there are actually 3 twofolds which got generated by the intersection of these mirrors. So, this completes the stereogram of the symmetry group M3 bar. That is why sometimes the complete notation for the point group in Hermann-Morgan notation is given as. So, now let us write the operations of this group, which should not be very difficult once we have noted the symmetry elements. So, the group M3 bar will consist of identity, and then there are 4 3 bar axes. So, corresponding to that we can write the threefold roto inversion operations, which for example along 1 1 1 I have 3 bar plus 1 1 1, 3 plus 1 1 1, 1 bar, 3 minus 1 1 1, and 3 bar minus 1 1 1. This corresponds to the operations along threefold roto inversion axes along 1 1 1. So, what I will do, inversion will be there along all of these. So, I will write it only once. So, I bring that here 1 bar separately, and then continue with my listing of the 3 bar axes without 1 bar, because 1 bar need not be repeated along other axes. So, this gives us 12 operations along the 3 bar axes, not counting 1 bar, which has been counted only once and has been listed. Then you have of course the mirror planes, and you have 3 of them. So, you have 1 0 0, 0 1 0 and 0 0 1. You notice that the intersection of these mirror planes in the twofold operations. So, you have 2 1 0 0, 2 0 1 0 and 2 0 0 1. So, this completes the 24 operations in this group. So, this is a group of order 24. So, we have completed the listing of cubic point groups, and with that we have completed also the listing of entire 32 point groups. In the future videos, we will look at some ways of classifying these point groups. So, for example, one important way of classifying is classification into 7 crystal systems. So, we will do that exercise in a coming video. Thank you.